Okay, welcome everyone to this week's webinar talk sponsored by the Chicago DOE Alliance Center. This week we're pleased that Levitas will be giving the presentation. Valeri is a distinguished professor in engineering with appointments in 3 different engineering departments at Iowa State. He's also a faculty scientist at Ames Laboratory. Valeri moved to Iowa State and Ames in 2008, and prior to that, he was at Texas Tech, University of Hanover, and at the Institute for Superhard Materials in Kiev, which at the time was a world-leading institute in that field, and where he received his PhD. Valeri is an expert in plastic deformation of materials, particularly at very high pressures, and uses both theory and experiments to address a wide range of problems with a principal focus on the coupling of plastic deformation and phase transformations, which I believe he'll tell us about today. And he does these experimentally with rotational diamond anvil cells and different kinds of simulations. So welcome, Valeri, and I'll turn this over to you.
Thank you very much, Russ, for invitation and for introduction. Thank you everyone for joining us. Title of my talk is Plastic Strain-Induced Phase Transformations under High Pressure for Scale Shear in situ experiments and phenomena. And I would like to acknowledge all my collaborators, students, former students, postdocs, and current funding. Well, I will start. Why it does not? Okay. I will start with insulting your intelligence and giving some simple definitions. So this is a schematic stress strain curve. If you are moving along this line, loading, unloading, and there is no residual strain, this is elastic deformation. If you go further and after unloading, we receive residual strain, this is plastic strain, we have hysteresis. This is essence of plasticity phenomena. And all metal forming processes are based on plasticity phenomena. And main mechanism is related to nucleation and motion of dislocations. Here you see dislocation pile up against grain boundary. And I will talk about this in detail. And also twinning, grain boundary sliding, and some others. Okay, now I will define phase transformation, displacive phase transformation as deformation of crystal lattice of low pressure phase or austenite in crystal lattice of high pressure phase or Martensitic, which is described by transformation strain tensor. In given case, this is cubic to tetragonal, and because of symmetry of cubic phase, we have 3 different crystallographically equivalent variants of high pressure phase. And this is a schematic of all 6 components of stress tensor. And when they work along, produce work along the transformation strain, this is main mechanical part of driving force. It's not just pressure volumetric strain, it's a product of all components of stress tensor on corresponding component of transformation strain tensor. And this is energy. Gibbs energy, this minimum corresponds to low pressure phase, these 2 to variants of high pressure phases. When minima are equal, then phases are in equilibrium. Then when we increase stresses, minimum for high pressure phase reduces, but there is barrier. And if this is low temperature and we neglect thermal fluctuation, nothing happens. So we need to further increase stresses and reduce minimum until this barrier disappears. And when this barrier disappears, low pressure phase loses its stability and transforms to high pressure phase. And this is barrierless transformation. And we will discuss, this is criterion for barrierless transformation. It's the same as phase transformation criterion for ideal material. So this is, someone probably will give completely different definition of phase transformation, but this works our purposes, and you know how firefighter distinguish between piano and violin. Piano burns longer, so this is sufficient. Well, I will discuss first experimental results in rotational diamond anvil cell, and then we'll discuss four-scale theory which we developed for understanding and interpretation and prediction of various phenomena under such conditions. At atomistic scale, our main goal is to determine lattice instability conditions. We just discussed them. This is the same as phase transformation criteria for ideal crystal, defect-free crystal. And we use molecular dynamics and density functional theory, also determine stress strain curves, elastic properties, and so on. At nanoscale, we study interaction between phase transformation and discrete dislocations. We using analytical method, molecular dynamic, but mostly we develop new phase field approach, which is very powerful for these purposes. At microscale, we develop completely different phase field approach, scale-free phase field approach, which allows us to treat much larger sample. And also we use micromechanics to derive kinetic equation for plastic strain-induced phase transformation. And this kinetic equation is part of our macroscale model, which we use to model behavior of sample under compression, traditional diamond cell, or under compression and torsion in rotational diamond anvil cell. Okay, so each high pressure lab has a diamond anvil cell. You see that sample within gasket or without gasket is compressed by two anvils. That is all everyone does. And using modern in situ techniques, one can study phase transformation and various processes in sample. What we are doing differently, after compression, we fixed force and superpose rotation of one anvil with respect to another. And this superposes large plastic shear, which actually changes everything. And this is similar to high pressure torsion. This is technological process. But what I want to say is that actually all what I will tell, plastic strain-induced phase transition, everyone also observes in traditional diamond cell under compression without transmitting media. So the same physics, kinetics, and we will discuss this. And even under hydrostatic conditions, after phase transition starts, there is large transformation strain, which causes huge internal stresses and plastic deformation. And again, interaction between phase transformation and plasticity is very important even under hydrostatic conditions. So what we measure? We use in situ synchrotron radiation to measure X-ray diffraction pattern. Based on them, and here based on equation of state, we measure distribution of radial distribution along sample radius of pressure within each phase in given case, and it's average over the sample thickness, but in each phase separately. This is example for phase transition for hexagonal to super hot versitic boron nitride. And it's very important to measure them separately because phase transition occurs in low pressure phase. So we need pressure in low pressure phase. And you see difference here, 6 GPa or by factor of 2. Also, we measure distribution of volume fraction of phases at different loading conditions, distribution of texture, distribution of different types of defects. In given case for layer, it's the graphite-like structure. This is concentration of turbostratic stacking fold, but it can be dislocation density. And using X-ray absorption, we measure thickness and profile of sample. Well, there are various phenomena caused by plastic shear, but I will focus on two of them. First, plastic shear plastic straining significantly reduces phase transformation pressure. For example, in this experiment, hexagonal boronitride, highly desodorate, was transformed to versitic boronitride at 6.7 GPa and rotation of 300 degrees. But under hydrostatic conditions, such phase transition doesn't occur even at 53 GPa. Similar rhombohedral, irreversible rhombohedral boronitride to cubic boronitride. It's 5.6 versus 55. So you see order of magnitude reduction in transformation pressure, and I will show even stronger reduction. Second, plastic shear leads to new phases which Venet and probably could not be obtained under hydrostatic conditions. And here is example of high density, new high density amorphous phase of silicon carbide, which was obtained at 30 GPa and large plastic shear, and under quasi-high GPa. Very recently, we found new desodorate super hot phase of boronitride. We detected it using X-ray and Raman scattering, and you see it cracks diamond, and even cubic boronitride does not crack diamond. Well, main theoretical problem is that none of these phenomena can be explained within classical macroscopic thermodynamics, even if you substitute pressure and volumetric strain with stress tensor and transformation strain tensor. So this is simple illustration. Here is mechanical part of thermodynamic driving force for phase transition. Pressure multiplied by volumetric strain plus shear stress multiplied by transformation shear. Problem is that shear stress is limited by yield strength and shear, which let's say 1 GPa. So if you apply 50 GPa pressure and let's assume such kinematic hypothesis, then you see that contribution of shear stress to driving force is just 2%. If we change here something in good direction, we can get here 10%, maybe 20%, but there is no way to explain reduction in pressure by factor of 2 to 10 and more. So that is why we developed completely different theory. Actually, it's 4-scale theory. Each scale describes corresponding features. And at atomistic scale, our main goal was to find phase transformation criteria. This is the same as lattice instability criteria, which I mentioned, and the action of all 6 components of stress tensor. This sounds like unsolvable problem because there are huge number of combinations of all 6 components of stress tensor, but we also developing phase field approach. And within phase field approach, we derived analytically expression for phase transformation criterion. So now we don't need to, we need just to check it. We don't need to exhaust all possible combinations. And this is doable and much simpler. So let's consider first loading. This is example for silicon 1 to silicon 2. It's cubic to tetragonal geometrically. And let's consider loading with 3 normal stresses, normal to phase, cubic phases. And this is our analytical phase transformation criterion. Sigmas are stresses, and some combination of stresses should exceed some threshold. Key point that this combination is linear in stresses. So in space sigma 1, sigma 2, sigma 3, it describes plane. Below this plane, nothing happens. When we reach this plane, a barrierless phase transition occurs. Then let's rotate this plane until it sees as a line. And then green dots here are results of MD simulation, and dots here are results of DFT simulation. And you see that both are in very good agreement with our prediction. And from fitting, we can find 2 unknown material parameters in this criteria. So then we apply all 6 components of stress tensor. We add 3 shear stresses. Criterion look more sophisticated, but in this additional term, there are no new material parameters. And also both MD and DFT show the deviation from our analytical prediction is within 5%. So now we have simple analytical expression for phase transformation criterion in ideal material on the action of all 6 components of stress tensor, and with just 2 material parameters which we calibrated. So this is, now we can predict phase transition at any combination of stress, of components of stress tensor. And this is well beyond from what was done in literature. Mostly maximum it was 2 components, 2 different components of stress tensor. Okay, and also DFT gives us stress strain curves at different loading conditions. Instability corresponds to maximum stress here. And also we found 5th degree approximation for elastic energy. That means elastic constants up to 5th degree. And you see here that our analytical stress strain curves, which comes from this energy, is in good correspondence with DFT simulation, including instability points, and for strains up to 35%. And previously, only sort of the elastic constants were known, and they were calibrated for strains below 3%. Okay, and I will mention only one result, that under hydrostatic conditions, this phase transition from DFT and from MD occurs at 76 GPa. Under uniaxial loading, it's just 11 GPa. So mean pressure is 3 times smaller, it's 3.7 GPa. That means it's 20 times smaller than under hydrostatic conditions. So extremely strong effect of non-hydrostatic stresses. But problem is that we cannot apply uniaxial 11 GPa to real defective material because yield strength is much lower. So how then we can use this knowledge? Well, we use it by introducing defects, and you will see now. Now we switch to nanoscale model, and well, one of point which was not recognized by high pressure community and by severe plastic deformation community, that there are 2 completely different types of phase transformation. It's pressure-induced phase transformation and plastic strain-induced phase transformation under hydrostatic conditions. So all of phase transformation in real material starts at defects. Why? Because defects produce stress concentrator. For example, if you consider dislocation pileup, at tip of dislocation pileup, all components of stress tensors are proportional to number of dislocations. So we may have quite large high stresses here. And pressure-induced phase transformation starts and occur at pre-existing defects. So for example, we apply 10 GPa phase transformation pressure for perfect material is 15 GPa, and let dislocation pileup consisting of 5 dislocation produce 5 GPa. So that means that in this region, pressure reaches 15 GPa and nucleation starts. But then pressure should be increased to activate nucleation at 4 dislocations pileup. Well, let's say pressure concentration is 4 GPa. So we need to reach 11 GPa. And so on. Then we need to increase to 12 GPa. And so you see that for pressure-induced phase transition, number of defects is limited, and that is why pressure has to be increased. And in contrast, for strain-induced nucleation, for plastic strain-induced phase transition, occurs at new defects which are permanently generated during plastic flow. And that is why we can keep pressure constant and increase plastic deformation and inject new defects and produce new dislocation pileups and new nuclei at tip of dislocation pileup. So pressure should not grow. But most important is that plastic strain-induced dislocation pileup may have much more dislocation. It can be 10, it can be 100. I showed in second slide, approximately 20 dislocation in the pileup. So all components of stress tensor can be very high here. And that is why one needs much lower pressure than for pressure-induced phase transformations. Also, what is important is that nucleation occurs in small nanovolume. And it's very probable that it's defect-free. And that is why shear stresses, or deviatoric stresses, non-hydrostatic stresses, are limited here by theoretical strengths, which is 1 to 2 orders of magnitude larger than macroscopic yield strengths. So actually shear stresses can be here 10 GPa, 20 GPa, and now they produce very large contribution, especially as we reduce external pressure. And finally, because such unique stress state with very high non-hydrostatic stresses cannot be reached in the bulk, because in bulk they are limited by macroscopic yield strengths, then there are chances that such stress state will lead to new phases which cannot be accessed under hydrostatic conditions. So this is main idea. Initially, I developed simple analytical model which described quite well many experimental results, but with a lot of hand waving. And now we are doing this much stricter. And this is, we developed phase field approach for these purposes. First for phase transformations, then for dislocations, then for their interaction. It took almost 20 years. And now we can study this, well, directly by solving differential equation. So let's consider model material with phase equilibrium pressure of 10 GPa. Phase instability pressure for perfect material is 20 GPa. And then we, for such material, we introduce one dislocation loaded hydrostatically, and phase transition occurs at 16 GPa. So now let's consider bicrystal under compression and shear. You see here the dislocation nucleated grain boundary and pile up against grain boundary, and produce here strong stress concentrator. And here these stresses due to tip of dislocation pile up fulfill our lattice instability or phase transformation criterion, which we obtain with atomistic simulation and used in our phased field model. So here barrierless nucleation occurs. And if we consider pressure average over this grain, it's just 1.2 GPa. So you see it's indeed more than order of magnitude below phase transition pressure under hydrostatic condition, and almost order of magnitude lower than phase equilibrium pressure, even phase equilibrium pressure. So it's deeply in the region of stability of low pressure phase. And if we increase shear, you see that there is growth, coalescence, and quite large red region is high pressure phase, quite large region transforms into high pressure phase. But here we neglect the dislocations in the right grain. If you introduce dislocation, you see that the transformed region is much smaller. So it's not straightforward. Plasticity always plays dual role. It promotes phase transition by creating stress concentrator, but it also relaxes these stresses and compete with phase transition. But we can find such combination of shear stresses and pressure that you see here results without plasticity in right grain, and with plasticity in right grain, you see dislocations here, practically the same. So it's controllable. And now I want to summarize this result as new possible routes for defect-induced material synthesis under high pressure. So instead of increasing external pressure, one can successively fill material with strain-induced defects like dislocation pileup, and they cause strong stress concentrator of all components of stress tensor. And because of large number of dislocations, it can be very high. And also deviatoric stresses are limited by theoretical strengths, which is 1 to 2 orders of magnitude larger than macroscopic strain. And first, this allows us to reduce external pressure to reach lattice instability. And also because of very high non-hydrostatic stresses, which are not reachable in bulk, this may lead to an access to new phases inaccessible under hydrostatic and quasi-hydrostatic conditions. So this is main results from phase field. We have also some confirmation from molecular dynamics. Here there is dislocation pileup. It's not shown. It's quite long here against 3 different grain boundaries in silicon and 60-degree shuffle dislocations. And for all grain boundaries, we obtain that the same curve, shear stress necessary for morphization versus number of dislocations. And you see that, for example, 8 dislocations can reduce shear stress from 9 GPa to 1.5. And of course, we can apply more dislocations. But also important point is that, again, not everything is good. That when we study screw dislocations, all of them pass through all 3 grain boundaries. So actually, they cannot pile up. They cannot promote phase transformations. Okay, now it's microscale. One of drawback of phase field, nanoscale phase field approach is that it resolves actual phase interfaces. And this is like 1 nanometer, and we need 4, 5 finite elements to resolve this, to obtain mesh-independent solution. That means, by definition, we cannot treat large samples. That is why we develop completely different microscale, scale-free phase field approach. And we combine this with plasticity, but we cannot combine this with traditional crystal plasticity because we still want to have our stress concentrator and dislocation pileups. And we introduce dislocation pileup through formulation of contact problem of continuum mechanics. So we cut it here. In many places, we introduce possibility to slip of one side with respect to another, like in contact of 2 bodies. And this reproduces continuous distribution of dislocation along slip planes. And it reproduces all required stress concentrator. And also, we were surprised, it reproduces our nanoscale results. But here we can study much larger samples. So this is polycrystalline sample under shear. And this is Retis distribution of Retis high pressure phase. And here Retis, actually it's volume fraction of different crystallographically equivalent variants. And you see here kinetics, phase volume fraction of high pressure phase versus shear in different grains. Very heterogeneous, and in some grains you see there is direct phase transition and then partial reverse phase transition. We also determined parameter average over the entire sample. It's how pressure varies with shear strain, shear stresses, volume fraction of high pressure phase, each Martensitic variants. And also we found very interesting results that you see this is simplest expression for phase instability, for phase equilibrium. Now we are not talking about nucleation, we are talking about stationary microstructure. So this is work of stresses on transformation strain, and it's equal to jump in thermal energy. Under hydrostatic conditions, this is just work of pressure on volumetric strain. And this condition, you see, there is nothing from plastic strain here. There is no surface energy. But if we come back, this condition corresponds to white lines. And you see these white lines. And practically almost all interfaces coincide with these white lines. It means that such simple phase equilibrium condition is satisfied at each equilibrium interface. And also, if you average the same condition over entire sample, it's also satisfied. And this is very important information and quite unexpected result. And all this kinetic equation and this information is currently used by us to develop advanced microscale kinetics for plastic strain-induced phase transformation. But currently we are still using our old equation, which also takes into account all what we learned at nanoscale in our analytical model. And for example, nucleation is barrierless, so there is no need to wait for thermal fluctuations. That is, time is not parameter. And plastic strain plays a role of time-like parameter. So kinetic equation is derivative of volume fraction of high pressure phase with respect to accumulated plastic strain. Also, dislocations, dislocation pileup generate both compressive and tensile stresses of the same magnitude, but in different regions. That is why they promote both direct and reverse phase transition in different regions. That is why we have two terms, for direct phase transition and for reverse phase transition. Also, when we get at least two phase mixture, plastic strain is very heterogeneous. So it localizes in weaker phase. And we develop very simple model which determines plastic strain in each phase versus average plastic strain and ratio of yield strengths of phases. That is why this equation includes actually a ratio of yield strengths of phases. And this equation, despite its simplicity, it allows to explain a lot of non-trivial and quite contradictory experimental results. But I would like to show our first quantitative confirmation. And actually, it took almost 15 years to get to this. Why? Because we cannot measure plastic strain distribution. That is why we could not use this equation directly. I mean, to calibrate, to check, but we use it in modeling. Well, now what we do, we are using assumption that we have the same kinetic equation for any type of straining. Is it plastic compression or any combination of pressure and shear? Kinetic equation is the same. This is very strong assumption. But if we assume this, then we can focus at the center of sample when there are no shears due to symmetry. And then accumulated plastic strain is just logarithm of ratio of initial to final signals. So we can know now plastic strain. And we study phase transition from alpha to omega phase in zirconium. So this kinetic equation contains, this is phase transition pressure under hydrostatic conditions. It's determined from separate experiment. And this is phase minimum pressure for plastic strain-induced phase transition. It's, by the way, we did not obtain reverse strain-induced phase transition. That is why we have only one term. So minimum pressure for plastic strain-induced phase transition was found to be 1.2 GPa. This is 4 times smaller than under hydrostatic condition and almost 3 times smaller than phase equilibrium pressure. Now you see here, this is pressure, this is plastic strain. And for 3 samples, there are 3 different loading paths. This is for poor compression, and this is for compression and shear. We can get phase transition under much lower pressure, as you see. And when you collapse all this experimental data in terms of this parameter, which follows from our kinetic equation, you see that they all along the same line, and this solid line corresponds to our kinetic equation. So indeed, this is confirmation of this kinetic equation. And also we found unknown parameters like K, W, yield stress was found independently, and confirm this kinetic equation. And by the way, one of important point to get such simple kinetic equation was confirmation of such equation, and simplifies drastically entire problem, is to preliminary deform material up to very high strain. At low pressure without any phase transition, but up to such strain that hardness and yield strength don't increase anymore. And then we obtain stationary microstructure. So this drastically simplifies. Then yield strengths are not function of plastic strain, and we can indeed obtain such simple equation. Now, what is also important, what we found, we use different magnitude of preliminary plastic deformation before phase transition, but results are independent of this. This is also very important. It should be higher than critical value to reach this saturation of hardening state, but then behavior is independent of preliminary plastic deformation. Also about minimum pressure for strain-induced phase transitions, this 1.2. You see here pressure distribution in low and high pressure phases, and these yellow squares correspond to initiation, so first detection of omega phase. And already it corresponds to the same pressure, 1.2 GPa. So you see here we have just compression without shears. Here we have very complex combination of compression and shear, but the result is independent of strain state. And this is very important. First, it confirms our hypothesis that we indeed can use our equation for any straining path. And practical value is that based on this, strain-induced phase transition under compression in diamond anvil cell and shear in rotational diamond cell don't differ in terms of kinetics, physical mechanism, and modeling, because we obtain the same results. And in contrast to traditional wisdom, it's not plastic shear, but any plastic straining produce the same reduction in transition pressure in comparison with hydrostatic condition. And generally, it would be wrong to say that shear reduces phase transition pressure in comparison with compression. So this is, I believe, quite important conclusion. Okay, and this kinetic equation is here, and it's part of our macroscale model, which I will not discuss. I will just mention that yield strength depends on pressure, plastic strain, and volume fraction of phases. And we use Murnaghan nonlinear elasticity rule. We solve maybe hundreds problem, and I will show only few results. So you see here experiment for Fullerian. This is before phase transition to Fullerian 4 and rotation. And this is stress distribution after rotation and phase transition. Force is fixed. Volume reduces by 35%. So everyone would expect reduction in pressure. But you see pressure grows. And this looks like a contradiction to Le Chatelier principle, but as I told, classical thermodynamics does not work for plastic strain-induced phase transition. And with our model, without any tricks, we reproduced, you see during rotation, volume fraction of high pressure phase increases in central region and pressure increases. And why? Because during compression at fixed force, this is quarter of sample. You see thickness reduces, and this compensates volume reduction due to phase transition. And also high pressure phase here is much stronger than low pressure phase. Then friction is higher also. And even if you use simplified equilibrium equation, pressure gradient is proportional to friction stress, then then the pressure gradient should grow during phase transition. And that is what is observed. And there are various other experimental results which are explained by this model. And now I would like to consider solution for just compression, hexagonal boron nitride which transforms to versitic boron nitride with an rhenium gasket. And we use our model for plastic strain-induced phase transition. And we use such minimum pressure for direct phase transition, which come for strain-induced phase transition, which come from experiment. And what does it mean? That if you will apply 6.8 GPa and large plastic deformation, we can not only start, but complete this phase transition. Okay, but when we compress, despite the fact that we have the same equation, plastic strain appears during pressure increase. We don't need this, we don't want this, but it increases. And actually pressure grows here faster than plastic strain if you can compare. And as a result of solution, we obtain that phase transition is not detectable below 12 GPa. And even at 53 GPa, there are regions with small plastic strain where phase transition did not even start. So what experimentalists would report? Exactly like this. Phase transition start pressure is 12 and it does not complete even at 53 GPa. But it has nothing to do with material behavior because we know that entire phase transition can be completed at 6.8 GPa if you will not increase pressure during our loading process. And if we change size, sample, thickness, gasket material, these numbers will be changed. So actually in such experiment, in 90% of experiments, what we report is system behavior, not material behavior. And practically what I showed you for zirconium, this is first characterization of material behavior because it was done based on local parameters and it's independent of surrounding and based on theory and calibration of this theory and verification of theory. And actually, what is the advantage of rotational diamond cell, despite the fact that physics is the same, that we can control loading path. And after some optimization for the same problem, I mean geometry, gasket, we obtain such a result that you see during quite significant shear and during phase transformation, pressure does not grow. So we can keep pressure constant and run phase transition by increasing plastic deformation. This is simulation, and actually we showed this before using simple analytical model, and then it was confirmed in experiment. So this is boron nitride, and this is pressure distribution. You see quasi-homogeneous pressure distribution after compression and shear. Next compression and shear. Next compression and shear and complete phase transition. So this is controllable, and that is advantage of rotational diamond angle cell. I promised to show you importance of plastic straining for pressure-induced phase transition, and even more at zero pressure. So this is just temperature-induced phase transition. You can apply pressure if you wish. This is phase transition in steel, very small volumetric strain, just 0.2%, but quite typical shear strain of 0.2%. Here we have large, I show part of large sample of low austenite, and this martensitic plate nucleates. You see this shear by 20%, it's visible. But after such shear, plastic deformation and surrounding already reach 46%. and in martensite, in austenite. In martensite, just maximum 8% because martensite is 3 times stronger. But then interface moves and inherits plastic deformation. And you see now plastic strain reaches 60%, both in austenite and martensite, and you see how strong deformation. It practically restores this 20% shear, but local deformation is 50–60%. And this plastic deformation drastically affects stress field here and arrest phase transition. So this shows that even under hydrostatic condition, or even without any stresses, still plastic strain occurs, and it strongly affects phase transformation. Now, so we want to determine distribution of all, we need to determine the distribution of all components of stress tensor, plastic strain tensor in, in entire volume in order to characterize phase transformation. And this cannot be done experimentally or theoretically. That is why we develop a combined procedure. And this is example, tungsten up to 400 GPa, just plastic deformation. And we use experimental data from this paper. And you see 4 pressure distributions, experimental, and 4 distributions of sample profile. Then we used our macroscale model and model these 2 situations and calibrated by fitting to this curve. And that's it. And then we made predictions for higher pressure, and you see quite good correspondence between theory and experiment. And also for all 4 profiles of sample, we have very good correspondence. And we did not use any geometric parameter from here to calibrate our model. So this is indeed very strong verification by 6 independent curves. And that is why we can claim that our model is robust and reliable. And that is why all data which we obtain, for example, pressure dependence of yield strength, it's much more precise than in previous publications. And I believe for the first time, pressure dependence of friction coefficient was determined up to high pressure. And actually friction stress is distributed very non-trivial. You see, for example, for 300 GPa at the center, this is region of Coulomb friction, very small region of plastic friction, and then adhesion, no relative slide. And if someone will use a method of measuring of yield strength and shear based on pressure gradient, there is only a very small region where this can be done. And of course, this is not reliable. Nobody knows where this region without simulation. And also we refined elastic constants for diamond by fitting because it's a very complex and large elastic deformation, third order, some 4th order constants, and no third order elastic constants for tungsten in Morgan potential. And now our results we can calculate based on a reliable model distribution of all components of stress tensor, plastic strain tensor, lattice rotation, and so on. Now, this is recent work also. Group from Berkeley developed method to measure distribution of all components of stress tensor along diamond culet. But not all of them were determined equally precisely. So shear stress was less precise. So our role here was that we did simulation and we fitted our simulation to good distribution of good components of stresses, and by this fitting we determine boundary conditions not only here but also at inclined surface. And then with this boundary condition we can produce distribution of stresses in the entire angle. And last result, shear-driven phase transition from graphite to diamond. I will talk only about cubic diamond. So under hydrostatic conditions, graphite phase equilibrium pressure for graphite diamond is 2.45 GPa. Lattice instability in ideal graphite is 250 GPa. And an experiment with real defective graphite, diamond is claimed to be found at 70 GPa. But with our phase field approach, we showed that this phase transition potentially could be driven just by shear and zero pressure. And then, motivated by this prediction, low pressure experiments was performed, and indeed, diamond was obtained at 0.7 GPa and moderate plastic shear. So this is 100 times smaller than under hydrostatic condition. And it was quenchable, so it's irreversible phase transition. And this is at the moment absolute record in reduction in phase transition pressure. I believe it also requires additional mechanism. I am not sure that exactly for graphite, just our mechanism can explain this quantitatively. And if this result is scalable, then it can be a basis for technology of low pressure of diamond synthesis. And also it may have implications in geophysics. And I will show conclusions, and I am ready to get questions. Thank you for your attention.
Thank you, Valery. Lots of very good material. Any questions for Valery? Just speak up, unmute yourself, or put a question in the chat box.
I have one question. This is Russ, this is Arjan. Valery, you showed one slide where you were talking about changing from in steel to Martensitic,
right.
Calculating, right? I was wondering whether that one, yeah, you just passed. That one, was this for pure iron or this is an iron?
No, this is steel. This is steel. This is alloyed steel.
All right. Do you remember what carbon content?
No, I don't. There are several elements, and I don't remember because it was almost 20 years ago.
I see.
But it's in this. But this is in this paper.
All right. Okay. Thank you.
Thank you.
Hey, Valery and Russ, this is Savine.
Hi, Savine.
From UCR and PNNL. Fantastic talk as usual. Okay, the last slide that you presented before the conclusion, that one got me a little bit because, you know, I'm a comic book fan and I've always seen the comic books where Superman squeezes coal in his hand and turns it into diamond. Or there's a DuckTales episode where elephants run over a field of coal and they all turn into diamonds afterwards. So, you know, this claim at the bottom is a really, really, really extreme claim. What this is basically saying is that even in conventional high pressure torsion, we should be able to convert diamond to, we should be able to convert graphite to diamond phase. So, can you be a little bit more specific on what the assumptions are for this very, very, very strong claim to be true?
Well, this is, okay, assumptions were in theory. This is experimental result, so there are no any assumptions. You compress, measure pressure, produce shear, measure pressure, and then you already detect in situ diamond. Actually, it was also hexagonal diamond, even at 0.4 GPa, but it was not quenchable.
It was not quenchable.
Was not quenchable. Hexagonal diamond disappeared, but cubic diamond was quenchable. And then, yes, it was also identified not only by X-ray, but by TM.
Yeah, so under these constraints, we could potentially do this even under high pressure torsion.
I think so. You know, it also probably strongly, not probably, strongly depend on initial material. And I believe in this case, somehow there was lack of for initial materials, because Blanc group did many experiments, but they mostly did at a much higher pressure. And this is smallest pressure where they can get irreversible cubic diamond.
Maybe if we started with some of Russ's highly defective diamond materials, but who knows?
Well, graphite, you mean graphite, yeah?
Yeah.
Yeah, well, it depends. This is a single result. Of course, it requires further detailed study and confirmation, but it is.
Okay. Great talk. Thank you.
Thank you, Savin.
As a follow-up, I'd like to ask you something. Is another way of really looking at this, and it relates to the diamond synthesis example here, is by introducing large plastic strains, you're introducing a large number of defects, as you say.
Right.
So if you look at this thermodynamically, when you introduce these defects, you're increasing the free energy. So in a strictly thermodynamic sense, it's the defective nature of the material, not necessarily the strain that's destabilizing it relative to the high pressure phase.
Absolutely right. So plastic strain, and I believe I told you this, plastic strain is a way to introduce strong defects, to introduce this, let's say, dislocation pileup with large number of defects, or disclinations, or nanograin structure. Maybe all of them contribute.
Right.
Yes, this is true.
Yeah, so that means in general, then, if you want to make these high pressure phases, the challenge is introducing those defects into the starting materials. And you could further test this by simply recovering the material that's defective and doing calorimetry to look at the true energy content. And then you'd have a whole new way of making high pressure phases at lower pressure, kind of independent of the strain part of it.
Not straightforward. And well, actually, when I summarize nanoscale result, I call this defect-induced synthesis, not strain-induced synthesis. So it's completely in line what you are saying. But if you introduce defects before phase transition, it may not help. It may not help. It should be during phase transition. And why? Because let's say you introduce dislocation pileup, right? But it can stress concentrator from dislocation pileup can relax through dislocations, right? And through twinning, through fracture maybe, and then it's not effective anymore. So you introduce a lot of defects, but they are like not effective stress concentrator. Mm-hmm. And then I would not interpret this in terms of energy average over something. It should be energy here, and not only energy, it should be loss of stability of parent phase or close to loss of stability. Because if you consider something in average sense, I don't see that there will be, I already did this, right? I believe I consider this in average sense, and I showed that you cannot get anything in average sense. So this is very local processes. Mm-hmm. This is like laser melting. Instead of melting entire big piece of material, you melt it point by point. Here, instead of transforming entire volume, you transform it small region by small region.
Okay. More questions?
So, this is Yang. So, yeah, I'm from Pacific Northwest National Laboratory. So I have a question. So you're using the dislocation pile-up model, right, to explain the local high pressure or shear to introduce induce the phase transition. So material under high pressure or severe shear deformation So at a water length scale, we can use in the dislocation pile-up model because yeah, under that deformation, maybe dislocation pile-up maybe like make the material amorphization. So really water length scale, we can really see the material, the dislocation is really the kind of individual dislocation pile-up. Can you make a comment?
Well, dislocation pile-ups are visible at, it depends on grain size, but for example, you see here in first slide, and you can Google dislocation pile-up and you will get a lot of nice pictures. So you see this is, let me check, I believe this is half of micrometer. And you see dislocation pile-up. Here it's even longer, I don't know scale here. So it can be at any scale, but mostly in our case, I believe this is at nanoscale. Why? Because after large plastic deformation, we obtain nanograin structure. So that is why dislocation pile-up should be like 100 nanometers, 50 nanometers. And also there are collective effects of dislocation pile-up. This can be shear bands. For example, strain-induced phase transition in trip steel occurs at intersection of shear bands. And then transformed region, this intersection has characteristic size of 100 nanometers, 200 nanometers. But this is not single dislocation pile-up, it's shear band, it can be intersection of twins. So, and you know, it can be also kilometer size in geophysical scale, right? If you have sliding, for example, here, this is scale 3. Let me show this model again. This is scale 3. It can be kilometer by kilometer, but this is localized shear bands. They also produce similar stress concentrator. If you have sliding of one piece with respect to another within bulk material, it produces stress field equivalent to dislocation pile-up. So it's a multi-scale phenomenon. Main physics is, I believe, at nanoscale, but it goes up to any scale and even to macroscopic shear bands.
Yeah, that's right. So yeah, also about the dislocation pile-up. So, so do you using the equilibrium profile of dislocation pile-up, or because maybe the dislocation really pile-up is not equilibrium, right? So they have a different distribution, and if we have a different distribution of dislocation, so you will get a very different dislocation stress concentration. So how that may affect?
Well, it affects. First, yes, we consider dynamics. That means that it evolves. It starts from, for example, here it starts from dislocation-free sample. Actually, we always start with dislocation-free sample. Then dislocation nucleate, number of dislocation increases, and we study this in detail. So, for example, for dislocation produce very small nucleus, then when number of dislocation increases, it grows. Then if they are close, they coalesce. But yes, it's a dynamic process. And here...
So when you apply to the real material process, yep. So how you really consider what kind of dislocation pile-up will form? Because using the crystal plasticity, we didn't have the really the dislocation like a configuration there, right?
Well, bad point is that we don't see this in experiment, that this model based on dislocation pile-up is poor theoretical prediction. So we know that there are dislocation pile-ups and we use them because this is the strongest concentrator I know. But there is no direct confirmation because it's indeed very small scale. And it would be great if someone can find method to detect this. Even at low pressure, it's not, well, it's not well proved. It's well known that Martensite nucleates are dislocations, but there are not a lot of clean works which show this. Because when you prepare, this should be TM probably, and when you prepare a sample, this large dislocation, well, pileups can relax. And well, I don't know experimental confirmation exactly of this mechanism. And as I said, it may be also different mechanism. And for example, in trip still, it's not dislocation pileup, it's intersection of shear bands. But based on this mechanism, we derived microscale kinetic equations. We explained many experimental results. We did predictions, which are confirmed, not directly, but indirectly and quantitatively confirmed. So it's plausible. That's all what I can say at the moment. And this is outstanding problem. And if someone can do something in this direction to find real stress, local stress concentrator near strain-induced nucleus, this would be great.
Yeah, thank you very much. Yeah, very good.
We have some questions in the chat. Speak up, Nikolai, do you want to ask your question? Okay, Maggie?
Do you hear me?
Go ahead.
This is a great application of quite universal methods to mostly simple materials, elemental solids. So my question is, can the same method be applied to slightly more complicated materials like binary nickel titanium, which happen to be shape memory alloy?
Generally, yes. Problem why, okay. The nickel titanium has zero volumetric transformation strain. That is why it's almost pointless to study it under hydrostatic pressure. But yes, the same method was applied. Actually, for steel, it's more than binary. I don't remember exactly, but it has 4 or 5 elements. So there are no limitations. But additional point, if you have alloying elements, plastic deformation can cause additional effect. It can lead to oversaturation in some regions or in entire regions. So you have additional degree of freedom, and this is completely, let's say, independent. No, it's dependent, but it's it has additional degrees of freedom, and it will be new science. The same for chemical reactions. There are experiments. This method is used for chemical reaction, for various reaction, decomposition, and reaction in polymers, polymerization reaction. So I believe that it's quite universal method, but in each specific case, result may be very specific. In addition to some general, let's say, first order theory, there are various very specific details. But general answer, yes, it can be applied to multi-component system.
Okay.
Well, steel is simpler in a sense than shape memory alloys. In shape memory alloys, there is super elasticity, where large deformations can happen without significant stress.
Right.
And
well,
shape memory alloys do have a super elasticity.
Right. It has, but that is not what we are interested in. Okay, let's put it in such way. All what you want to say about shape memory alloys, this is stress-induced phase transition. This is stress-induced, not plastic strain-induced. If you will start plastic strain-induced phase transition in shape memory alloys, you will spoil effect. So this pseudo-elasticity will be destroyed. And actually, there are many papers when preliminary plastic deformation is used to increase hysteresis and for example, for energy absorption purposes. Yeah, so if you want to talk about shape memory alloys, real applications, this is not good method because it actually spoils some of effects. It increases hysteresis, it increases energy absorption for shape memory alloys. But you don't need high pressure. You can do any plastic deformation, traditional method, it will work. And that is what is done in applications for shape memory alloys. It's called Aus forming, Mar forming. This is plastic deformation of austenite or plastic deformation of martensite. And this also controls martensitic transformation, stress and temperature.
Okay. A few more questions if you're interested in staying on.
Hi, can you hear me?
Go ahead.
Yeah. Okay, yes. So this question is regarding the, this is Mageshwari from PNN. So this question is regarding the minimum pressure for direct strain-induced transformation. The pressure reduces as a function of plastic strain. So I'm interested in understanding the effect of temperature. So maybe after a certain temperature, the recovery process might not like lead to reduction in pressure for strain-induced phase transformations, but below the temperature, what do you think the effect of temperature would be? Like, does it aid in even increasing the pressure further, or does it increase the minimum pressure for phase transformations?
Okay, general answer. If you are above recrystallization temperature, then the effect cannot accumulate. You cannot produce dislocation pileup or any strong stress concentrator. They will, material will recrystallize and annihilate them. So limit case, if you are above recrystallization temperature, this method will not work. At lower temperature, it depends on many parameters. So it depends whether temperature itself promotes phase transition or suppresses phase transition. But bad point is that temperature usually reduces yield strength. And that means that non-hydrostatic stresses will be well, limited by lower yield strength. And also it may activate different mechanisms of stress relaxation, like diffusion, and then instead of getting our phase transformation, creep may reduce stress concentrator due to dislocation pileup. So that is why we did not study effect of temperature, but group Vladimir Blank from Troitsk, they studied well, at least I remember some experiments at slightly elevated temperature and at cryogenic temperature. I don't remember honestly comparison how this effect works for different temperatures. I don't remember, but generally increase in temperature should reduce this effect and finally eliminate above recrystallization temperature, and reduction in temperature should promote this effect.
Okay. What is the last name of that person that you just mentioned, Vladimir?
Okay, it's, I believe that recording will be available, and his name is in last
Okay, yeah, I can check
slide,
it.
Blanket.
Okay, thank you.
So why don't we take one more question?
Hey, hi, Valerie. This is Arun Devraj from PNNL. Great talk as usual. So one question on the continuation on the temperature aspect of it. So what about the deformation-induced heating? I know that your strain rate is not too high, that you are generating a lot of heat in most of your experiments, but and the diamonds can actually quench the heat rather quickly. So can you comment anything on in our cases where we are rotating very fast and with diamonds? Any comments on how that heat extraction will happen and what role it might play into all of these observations?
Okay, in our case completely, because of reason you said, but as I remember when we discussed this with you, you told me that actually even at high strain rate, so it was like, I don't remember, 100 rotation per second or 1000 rotation per second. Also, you said the temperature increases just by
1 degree or so, yeah.
few degrees, right? Okay, I don't have any additional information, and I believe your information is the first one in this field, effect of. And this is really great because, you know, people struggle when they study viscoplastic behavior of material, how to separate effect of temperature and strain rate.
Yeah.
Because here there is no temperature increase, it's possible to find strain rate dependence and strain dependence at any prescribed temperature. This opportunity. It's not easy, it's a very difficult would extract this information at high strain rate, but probably it's doable. Maybe you will.
Great. Thank you. Thanks a lot. Thanks a lot for the great talk, and thank you for organizing.
Thank you for the question. Okay, well, thank you, Valery, for an excellent talk. Lots of good discussion. We'll be posting this recording. If any of you are not on the mailing list, just send me an email and I'll put you on the regular mailing list for this weekly seminar series. So thank you all for joining us.
Thank you very much, all. And Russ, again, thank you for arranging and for inviting. Bye.
Thank you. Bye.
Bye-bye.